welcome to Quantum Photonics. We have a very exciting episode today with our special guest, Dr. Kamyar Azzizadenesheli. Kamyar's research interest is mainly in the area of machine learning from theory to practice. He works on topics including but not limited to reinforcement learning, um, bandits to MPDs, POMPDs, etc., and applied mathematics, deep learning, neural operators, control theory, spectral method, optimization, high dimensional statistics, risk assessment, online learning, domain shift, active learning, safety, adversarial attacks, and generative models through both learning theory and core scientific lenses. Kamyar is research scientist, and prior to his work as a full-time research scientist, he was assistant professor at Purdue University, Department of Computer Science from fall 2020 to fall 2022. And prior to his faculty position, he was at California Institute of Technology, Caltech, as a postdoctoral scholar in the Department of Computing and Mathematical Sciences. Before his postdoctoral position, he was supported as a special student researcher at Caltech, working with machine learning and control researchers at the CMS department and the Center for Autonomous Systems and Technologies. He is also a former visiting student researcher at Caltech. Kamyar Azzizadenesheli is a former visiting student researcher at Stanford University and researcher at the Siemens Institute, UC, um, England, and New York. He received his PhD at the University of California, Irvine. So, yeah, I excitedly introduce to you our special guest speaker, Dr. Kamyar Azzizadenesheli. So, Kamyar, welcome to Quantum Photonics. I hope you will enjoy your first clubhouse experience in terms of, telling us, about your work.
Well, thank you so much, Cecile. Thank you for a great introduction, and thanks for having me. It's a great pleasure to be here, and hopefully my first clubhouse experience would go as we want it to go. So, Cecilia, you want me to start talking about the topic?
Uh, yes, sorry, I forgot to unmic. So yes, please, may we start? I would just like to tell the audience also that I will be posting the copy of the paper of one of the papers of Kamyar here at the room chat, and yeah, there was also a popular article about that. So yeah, we are very excited, Kamyar, to hear your presentation today. So we can start to hear your talk now. Thank you.
Yeah, thank you so much. Yeah, at any time you guys hear that I barely hear me, or you feel internet connection has some problems, just please let me know. So, thank you everyone for joining the clubhouse. I hope that we can have an interactive conversation about the topic that I'm going to bring to the stage today. So, the topic I'm going to talk about is called neural operator. For those of you that are familiar with deep learning and neural networks, this topic is a slightly different than neural networks. This is still a deep learning setting, but it's slightly different than traditional neural networks. In the sense that traditional neural networks are maps between finite dimensional spaces. Let me give you an example. You probably have seen many exciting results in deep learning, which people actually take like as an input. They take an image, which is like 128 by 128 matrix, and feed that input to a neural network, and the neural network outputs a category, a class, a label, or another image. Okay, so most of the neural networks we have seen so far are basically mapping between like images, mapping from images to a bunch of numbers. You have seen DALI, which maps words, which are again finite dimensional objects, and images to images. So basically, almost all the deep learning we have seen so far were about learning maps between finite dimensional objects. By finite dimensional objects, I mean things that we are mainly familiar with. Word, like image, all of these objects are, but like there are finite number of numbers that we use to represent these objects. So basically, when I say finite dimensional objects, I mean we use finite dimensional numbers and fixed number of numbers to represent the input and output. Okay, so what is neural operators? For neural operators, we want to go a little bit beyond this I would say 100 years old paradigm of neural networks. And instead of learning maps or working on maps between finite dimensional objects, I want to do something a little bit crazy. I want to take everything to infinity. So I want to have a map which instead of being mapped between finite dimensional spaces, I want a map that is actually a map between infinite dimensional spaces. In other words, I want to have a map or deep learning model which as an input receives an infinite dimensional object and outputs an infinite dimensional objects. Okay, might sound like fairy tale. Well, let me give you an example. What is an infinite dimensional object? A function. If I give you a function is an infinite dimensional object. Okay. So in neural networks, we were trying to learn functions which were maps between finite dimensional spaces. But in neural operators, we aim to learn maps between function spaces themselves. So again, in neural network, I have a function as an input receives few numbers and outputs a few numbers, right? So I try to learn a function which does this map for me. In neural operators, we actually want to learn an operator which learns maps between the functions themselves. It's going to be a function, output is going to be a function. And now you might say, hey, Kamyar, why we care about such a thing? Why this actually matters? What is the application of uh, such a futuristic like idea of having maps between infinite dimensional spaces or function spaces? Let me give you a thought experiment that you can actually run at your place right now. Consider the wall behind you. That wall, let's say I have some device which I can set the temperature of that wall however I want. So there is a wall behind you. I set the temperature of that wall however I want. That temperature is a function defined on that wall. Any point on that wall you look at has a temperature associated to that point. So that now, given that temperature function on the wall behind you, I want to know what is the temperature behavior inside the room you're right now in. Okay, so then what I'm interested is like I set a temperature on the wall, which is a function on the wall. At any point, I would get different temperature. I set that, and after setting that temperature, I'm asking what is the temperature behavior or temperature profile inside this room you are actually right now at. Okay, so the map I'm interested in this problem is a map from a function defined on the wall to a function defined on this 3D room you're actually in. So this is one example. You might say, hey, Kamyar, this is a toy example. Sure, it's a toy example. Let me give you another example. I tell you the temperature, pressure, velocity of the air on the surface of the Earth. And given this, which is a function defined on the surface of the Earth, I would say what is the weather condition in 6 hours, which is another function on the surface of the Earth. And the map we are actually interested here is a map from a function defined on the surface of the Earth to another function defined on the surface of the Earth. So another problem that we actually need maps between function spaces is in weather forecast. In weather forecast, I tell you what is the weather condition of the Earth right now, and all these weather services and like national weather forecast models or centers, they take this function as an input, and they do many operations to tell us or to forecast or predict the weather in next 6 hours or next 10 hours or 12 hours or next few days. Okay, so the weather forecast problem is actually a problem of mapping from function to another function. I can give you many more examples of the maps we need, but the problems that actually we are interested in maps between function spaces. But I can tell you that almost all the problems in scientific computing are about coming up with maps between function spaces. Okay, so what is neural operator? So in this problem of learning maps between functional spaces, we haven't had anything in deep learning to do such a thing. Neural operators are a new technology that allow us to learn such a map. Okay, so now I can use neural operators, and given the data of, let's say, last 40 years of weather, see at any hour or at any moment what is the weather, and see how was the weather in 6 hours after that, and collect a data set of input and output and train my neural operator, which actually learns to predict the future. So this is basically the concept of neural operator, which is mapped between function spaces. Yes. So you might say, hey, Kamyar, I'm talking about weather forecast, and I'm saying that, hey, for weather forecast, we probably need neural operators, and neural operators can be applicable in weather forecast or many other scientific application that requires maps between function spaces. But you might say, hey, Kamir, so far we have been doing this maps for forever. Like weather forecast like humanity has been doing weather forecasts for like the last many years. Or humanity has been trying to come up with, like, if we set the temperature on the wall, can we come up with the temperature in the room? We have many methods to do this calculation. There are many partial differential equation solvers. There are many computational solvers in industry and academia. Many places there are lots of solvers. We have been using the solvers forever. Why we need neural operators when we actually we have solvers? Okay, so this might be a fair question, but let's see what are the solvers. The solvers, in order to solve a problem, they need to have access to an equation. Okay, so if for example, for weather forecast, I need to solve many PDEs. Basically, a PDE with many equations. PDE stands for partial differential equation. Basically, partial differential equations are basically the foundation of many of the scientific application. If you want to see how, if you set a temperature on a wall and you ask what is the temperature in the room, you need to solve the partial differential equation to come up with the answer to this question. However, the methods, the solvers that actually solve for such problem, they're extremely slow. So if you tell me the temperature on the wall behind you and ask me what is the temperature inside the room, in order to solve this, I need to do a ton of calculation to see what is the temperature inside the room. Okay? And after solving this, now let's say I set the temperature on the wall to some function and you solve for it and you tell me what is the temperature inside the room. And if I change the temperature on the wall to something else, you need to run this calculation again and wait for 2 days that you get the results, and that result will tell you what is the temperature inside the room. If I change this 100 times, you need to run this computation 100 times. And the fact that now you have run this computation like 102 times does not change the fact that how you would solve this problem if I ask you the same question one more time. Okay, if I give you another function which represents the temperature on the wall, you need to call the solver that you have again, and you need to spend 2 days and wait for the solver to solve this problem for you. And the fact that you have already solved this problem many times does not affect the fact that the way you actually solve the new function. Okay. However, if I'm able to do learning, if I'm able to learn this map from the temperature on the wall to temperature inside the room, if I'm able to learn that next time if someone gives me a temperature on the wall, which is like somewhat similar to temperature I have seen so far, I can just call the neural operators to predict the solution. I don't need to solve them anymore. Okay? So if I have a solver, given the temperature on the wall, I can call the solver. The solver can give me the temperature inside the room. But if I do this operation like 1,000 times, I can use the data, train a neural operator, and given that neural operator, if someone gives me new temperature on the wall, instead of calling the solver and wait for 2 days to get the answer, I can just call my neural operator to predict the solution, and it takes a fraction of a second. Okay? So now think about this in a weather forecast setting. For last 40 years or last 60 years, we have been having the nope.
To This is Bob. We lost your sound for a moment, about 10 seconds or so.
Okay. So you hear me now?
Perfect.
Yes.
Okay, great. So what I was saying, let's repeat this example I just talked about to weather forecast. In order to forecast the weather in next 6 hours, this big, gigantic supercomputers are run in this big government-funded agencies, and they are able to tell us after running a humongous computation for hours. They're able to tell us what is the weather, let's say, tomorrow. Okay, so in order to predict the weather for tomorrow, they need to run these big equations, big machines, big supercomputers, in order to tell us what is the weather tomorrow. And as you may know, the weather tomorrow has a ton of variation. In order to capture that variation, they need to run the solver many times. Okay, so they need to have many CPU and GPU nodes, a big supercomputer that they can run in parallel, and they need to solve this gigantic partial differential equation that they have, which allows them to predict the weather in next 1 day or 2 days in parallel for multiple runs to see how the weather in like 1 day or 2 days would be. Okay, so this is like how we are doing it right now. But now let's for a second imagine that hey, we have 40 years of data worth of data about weather, and we have these solvers. They keep predicting the solution or the weather in the future. Can we use all of these to actually train a neural operator which can predict the weather of the next day or 2 days or like the next week instead of in hours on these big supercomputers they run on CPU? Instead of that, can we have a neural operator which actually can do all of these things in like less than a minute? Yeah, the answer is yes. You will see like there are so many problems in scientific studies and scientific computing that they require building very complex solvers that are basically there to solve a bunch of complicated and handmade, basically, and hand designed partial differential equations in order to do some prediction. Okay, so now we have access to data. We can actually go and use neural operators to tackle all these problems that these traditional methods were trying to tackle with the speed that never seen before. Okay, the speed of these neural operators after they are trained is so fast that we have been solving some problems recently that they were thought they were actually doomed to be unsolvable by biggest computer that the humanity ever built. So the speed of these neural operators and also these deep learning models and the memory consumption, the minimal memory consumption of these deep learning models actually enabled us to tackle many big problems that in the past they were almost impossible to think about. Okay, so these are like basically neural operators. They are there to learn maps between function spaces, and majority of scientific computing problems are based on mapping functions. And for all of these problems, neural operators can chime in and help us to speed up all these computations by like multiple orders of magnitude. And just for a second, imagine that many of these big computation and problems that humanity solves these days, imagine all of them in one day, they can be solved like 3 or 4 or 5 orders of magnitude faster. And imagine how much more science we can develop, how much more um, trustworthy science we can actually develop. All this, let me give you an example of why I'm talking about trustworthiness. In weather forecast, there are many scientists, they put a ton of hours to come up with these partial differential equations. Basically, they try to model the atmosphere. And after they try to model the atmosphere based on many parameters that they had to tweak and tune, they can actually solve those equations and predict the future. However, all those models are in the end models that human put there. Many of the parameters there are like hacky and heuristic parameters. Some of the algebraic part of those equations are actually by choice that few people they had to come up with like 30 years ago. So we are actually relying on those models. However, if we use neural operators for weather forecast, that neural operators are trained on real world data, then we actually have trustworthy prediction models. We don't have to use this last generation of prediction models, which are based on these partial differential equations. Since we can actually use the real world data, we can train our neural operators to do weather forecasts for us. And now we actually have a trustworthy model. Okay, so we don't need to use hacky approaches developed in the past. Not hacky, well thought, ton of hours, highly tuned, and many amazing scientists spent time to develop these weather forecast models. However, in the end, they have many limitations because we had to make so many simplifications for those weather models in order to make sure that we can actually do something with them. Okay, I'm not saying those are basically hacky. Those are great efforts that humanity put there, and we have great weather forecast systems these days. But neural operators can actually circumvent all the limitations they have and basically make no approximation and make sure that we actually learning to predict the weather as is not changing anything with respect to that. Okay, so these are like basically this is basically what is neural operator, which is maps, and we can use many we can use them in many settings and in scientific application. We have used these neural operators for weather forecast. We have seen a great excitement in both sectors of industry and academia to incorporate more knowledge to neural operators to advance weather forecast problem. We have used them for material sciences, where you can use them to see how material deforms, which is another scientific application which involves maps between function spaces. There's another application that I think I'm very optimistic about and I'm really excited about is about ways we can inject CO2 under the surface of the Earth. So let me tell you what is this problem. This problem is, so these days, as you know, we have so much CO2 wandering around in the atmosphere. There are some companies that collect this CO2, but we need to actually, after collecting them, we need to store them somewhere. And one of the most efficient ways to store them is storing them under the surface of the Earth. Okay, so we take CO2 and with some pressure, pressurized material, we engine, we inject CO2 under the surface of the Earth. And now the question is, hey, if I want to inject CO2 on the surface of the Earth in like San Francisco, is it a good idea? If I inject it, can I inject how much CO2 I can inject? I need to build all this facility and try to inject CO2 on the surface of the Earth. Is it a good idea to do it in San Francisco? If it's not, is it a good idea to do it like 50 miles north of here, or I don't know, in some Sacramento or any other area around the region? And all these questions are basically they boil down to the question that given an area under the surface of the Earth, how much CO2 I can put there. So area under the surface of the Earth is represented as a function which actually tells us the structure of the rocks and water and permeability of the Earth there. So these are actually functions that represent the area under the surface of the Earth. And given that, I want to know how much CO2 I can store in all the points in the under surface of the Earth. Okay, so this is a problem that I need to solve, which is a map from the structure of the under surface of the Earth to the CO2 distribution after I inject CO2 there. Okay, so now I want to decide where to dig and make a reservoir for myself in order to inject as much CO2 as I can that have a cost-effective benefit to me. So in this case, I need to call all these partial differential equation solvers that I have, and for each region, I need to solve this partial differential equation, which tells me, given the structure of the Earth, how much CO2 I can put in this location of the Earth, how much CO2 I can put in that and the next location of the Earth. And for each of them, I need to wait like days and days to solve for this question. Okay. However, if you use neural operator, you can just do this map in like a second or two, and you can actually test many places like around the Earth and find the best place you want. So imagine a process that used to take like years to be done. It can be now done in like a day or two. This is like crazy. Like amount of speed up we are providing. These neural operators actually provide in the sectors of technology and research is like beyond imagination. At least to me. Yeah. So there are many other problems we can talk about that neural operators have been already used and people are developing more methods in. Is one of them is seismology. In seismology, if I have an earthquake somewhere, I want to see how the earthquake wave propagates under the surface of the Earth and reaches different places with what magnitude, right? How you represent the under surface of the Earth is a function which is in like 3D dimension. For each location or position under the surface of the Earth, you need to tell me how wave propagates there. Okay, basically what is the wave velocity there, or something in that sort, or what is the material of the Earth and that location. If you tell me all of these, then given an earthquake, we can actually solve a partial differential equation, basically wave equation, which tells us how wave propagates under the surface of the Earth. So now if I have a neural operator which is trained on this data, given an earthquake and a velocity or a structure of the Earth, I can actually, in a fraction of a second, predict the earthquake or the propagation of the earthquake under the surface of the Earth, and this actually allows me to do many predictions. Okay, and also you can think about the very niche and interesting problem. Now that you have seen many earthquakes on the surface of the Earth, you can ask, hey, what was the velocity that cause all this wave behavior for these earthquakes. So this way, if you have an observation, you have many observations of earthquakes on the surface of the Earth, on it. Given those observations, we call them seismogram. You can actually go and infer what was or what is the structure of the Earth under the surface. We can actually do many geological like a study in that respect. Yeah, so I hope that I was able to motivate you guys about the importance and significance of neural operators and how they're actually shaping the future of technology and sciences. And it's a great time to know about them and what they are capable of, and the bigness of the impact they can have in next like a decade in many sectors of scientific computing and also engineering computing. Yeah, thank you so much. I would be happy to take any question.
Yeah, thank you so much, Kamyar, for the great presentation. And we would like to open the floor to questions if you have any questions. So it was very informative for us. And yeah, I would like to ask you later about we have some guests here who are recurring, and they're working in the Oak Ridge National Laboratory, and their research is about material science and also imaging, wherein they're trying to leverage optical imaging using now machine learning to discover more materials and yeah, to do the engineering and design. So probably I can connect you. Have you ever worked with these people? Have you ever collaborated with these people?
I've never been fortunate enough to collaborate with the people you mentioned. However, I have quite a few collaborations with material scientists that I basically enjoyed a lot, and I think the problems they are solving are so one of the problems I mentioned in my presentation that humanity could we actually most of the scientists were like they gave up and thought that given the computation power we have, we can't solve these problems. That using neural operators, we actually have been able to easily solve them. That problem was actually a material science problem. So problems in material sciences are extremely hard and are extremely heavy in terms of computation and basic compute powers. And these problems are actually one of the sets of problems that neural operators going to make big impacts because they can actually allow scientists to solve the problems that they have been trying to solve for last like 50 or 60 years.
Yeah, thank you so much. So, yeah, later on I have another question and some comment. In the meantime, I would like to give the floor, the first privilege to ask you if he is available to Dr. Hansen Chen, who introduced me to this topic and had requested that we invite you here in Quantum Photonics. So, Hansen, are you able to speak now?
Yes, indeed. Thank you very much, Cecile. Thank you very much, Kamyar.
Hey Hansen, I
Hey, how's
see
it going?
Erdo's picture on your profile.
Yeah, Erdos and Terry Tao.
Yeah.
Yeah, they're the great mathematicians. And actually Terry Tao isn't far away. I mean, I guess you're not at Caltech anymore right now, is it?
No, I'm in SF right now.
Oh, okay, yeah.
Yeah, but I visit there often.
Quite often, yeah. It's not too far from there.
Right.
Well, it could be far in terms of traffic, I guess. So it's great to have you here. And actually, I did suggest to invite you because I am quite interested in the mathematics of neural operator. So I actually would, if you could, get into more details of the technical details of the subject. Particularly, I would like to know the application of Fourier transform to the neural network, and whether the the uh, uh, the effect of the Fourier transform is it to make the scale, make the connection between the smaller scale to the larger scale, and if it is, then would it be correct to assert that Fourier transform would be just one of the many method to use? For example, you maybe wavelets would be applicable, and also maybe fast multiple method would be applicable as well. So yeah, so let's start with these questions, and I have a lot more to come.
Oh, certainly.
Thank you.
Thank you so much. Yeah, thank you so much for the question, Hanson. So regarding technicality of them, so let's in order to go over the details of neural operators, let me just say what is neural network. I'm sure all of you guys know. I just want to set the terminology. So a neural network, let's say I have a feed-forward neural network. The input is a vector. Then given this vector, I multiply this vector with a matrix. So I would do a linear transformation of the vector, and then I would add a nonlinearity on the top. Let's say sigmoid, ReLU, these are basically nonlinearity I would on the top. So in neural networks, I have a vector as an input. And then I have a matrix, which constitutes the parameters of the neural network. And I apply this matrix on this vector, which is basically a linear transformation of the vector input vector to another vector. And then I apply nonlinearity on the top. I'm simplifying the neural networks a lot here. What is neural operator is basically the same thing, but neural operators we make a distinction between neural operators and neural networks. Neural operators are generalization of this operation. So input, instead of being a vector, now input is a function. And since we have a function, the same linear transformation that we had in neural networks, which was given a vector we multiply by a matrix, which is a linear transformation of the vector. In neural operators, given a function, we do linear transformation of the function. What is a linear transformation of the function? Is like integral operator. Okay, so you just apply an integral operator on input function, and it outputs another function. What is integral operator? It just take the matrix and make it as wide as possible, and and take the width of it to infinity, and like the depth, what's called height of it to infinity. You would and then think about multiplying an infinitely long vector with this infinitely big matrix. It gives you infinitely long vector, and that vector is actually our function. Okay. So
yeah, so that would be, sorry, just to interject. So that would be just basically the Riesz representation theorem. Right?
Yes, exactly. So I basically take an integral, which integral operator has a kernel in it. So integral of k of x and y d mu, and that mu, which is a measure I'm going to compute the integral, comes from the Riesz representation theorem, which says for any linear integral we have such a mu. That's exactly what happens there. Okay, so this one gives me, given an input function, I apply this linear transformation on this input function, which is a linear integral operator, and it gives me a function in the output, and I apply nonlinearity on the output function. This is basically one layer of neural operator. So now this kernel integral operation I was talking about, if I replace the kernel inside this integral operator with a convolution kernel, okay, so instead of having k of x and y and doing integration, let's say over y, I wish I would have sent you. Oh, actually, you can go to slide number 11. if you guys have access to it. If you guys have access to that, given a function v, which is an input, the first thing I would do after receiving the function v is I would do integral of this kappa x and y vy d nu. Okay, so this is an integral operator. If I replace this kappa x and y with kappa x minus y, basically make it shift invariant, this becomes a convolution operator. Okay, and if I have a convolution operator, I can write down this integration in Fourier domain. Okay, so now basically instead of computing this integral, I can compute the Fourier transform of the kernel and Fourier transform of the input function v, and do multiplication in the Fourier domain, basically invoking the convolution theorem, and do multiplication in Fourier domain and do inverse Fourier to compute this integral. So this is basically Fourier neural operator, which is basically does this integral computation in Fourier domain. So Hansen, you have this question that can we use wavelets to compute this integral? Of course. Yeah, we can use wavelets. We can use any noise storm approximation method we have developed in the last 200 years, or I would say 300 years. Even Gauss quadrature methods, we can use all of those to compute this integral. Whichever you want, we can do it. And you also brought up multiple approaches. Actually, the second paper I wrote about neural operators is actually about multiple. So multiple is another way to compute this integral.
Great. Yeah, great. So the question would be, so basically the convolution operator naturally leads to the Fourier transform, because you basically the Fourier transform convert it into an algebraic problem. But
Yes.
great. Yeah. The natural question would be, is it do you have a theorem saying that any operator could be approximated arbitrarily closely by the convolution operator?
Okay, so we have one theorem which says any operator that is mapped between space of periodic functions can be approximated by this convolution theorem style operators. So if the input function is periodic, okay, let's say you have a temperature on the surface of the Earth, which is like, you look at it in a lateral sense, it's periodic. Or you have any periodic function as an input, and the output is also a periodic function. In that case, any operator can be approximated by Fourier neural operator. But if you go beyond that, we still don't have the theory for it. But we know that any operator can be approximated by the generic form of neural operators I have on slide 11, but not FNO for now.
Got you. So it's if you have a finite region, then if it is the boundary condition is periodic, then you can approximate it with the convolution neural network and convolution operator, and therefore the convolution neural net, right?
No. So we can, if you have a periodic boundary condition, then you can. The theory says there exists a Fourier neural operator which can approximate any operator there. However, in practice, you don't have to have periodic setting. Even if the boundary conditions are not periodic, you can still run. We don't have the theory,
Sure.
but we have run yeah.
Oh, okay. Yeah. No. Okay. Go ahead. I suppose you were saying that in practice, even without the guarantee of a theorem, but in practice, you get very close. I mean, very good approximation. Is that what you're trying to say?
In practice, it works very well. So in theory, we haven't proved it yet, but it doesn't mean that it can't approximate it. In practice, we have seen that it approximates everything very well with no problem so far.
I see. And then also in practice, I mean, in theory, suppose that, for example, suppose you have a very kind of rectangular or hypercube region, then you can just extend it and then make it a larger maybe let's say reflection or translation, and then make the larger domain periodic, right? The function.
That's exactly what we do. We do it two ways. One of them is by padding, similar things that people do in convolutional neural networks, which actually pad the input image with some zeros. Here we pad input function with some zeros to make it periodic. Another more elegant way that we do it is called Fourier continuation, which is exactly what you said. You actually you take the input function, which is defined on the rectangle or hypercube, and you expand the domain, and between you actually continue your function such that the whole thing becomes periodic. In that sense, the Fourier neural operator would get is universal approximator.
Right, and then just question: if you just go ahead and do it, would you have let's say Gibbs phenomena when you have the discontinuity across? Let's say even if let's say you have a discontinuous region, let's say slit or something, would you have the Gibbs phenomena that which is basically a ringing noise generating from applying Fourier transform?
Yes, you are actually touching upon a very, very important point. If the input function is not continuous, has this jumps in it, yeah, if you use Fourier methods, we are going to have some difficulties in terms of Gibbs phenomena. That definitely would happen.
I see. So, so the effect of the Fourier transform, is it to connect the scale multiple, make the connection between multiple scales? I mean, as opposed to not applying the Fourier. I mean, so my question is, why does the, let's say, convolutional neural network itself does not resolve the problem, and then until you inject the Fourier transform or the wavelet